This video is just going to tie up some loose ends with respect to acids and bases. So we're going to start by talking about the pH of water. So you always think of the pH of water at 7 as 7, and that's because we usually will talk about it at room temperature. If we raise the temperature, it goes up, the pH goes down. If we lower the temperature, the pH goes up. So let's talk about why. So the Kw reaction is this right here, okay? And it's going to take energy to dissociate the water. So we put energy here. It's an endothermic process. At 25 degrees Celsius, the ionization, meaning this, the breaking apart of water, is very small. And our Kw is 1 times 10 to the negative 14. That's a very small Kw, so we don't have a lot ionizing. If we lowered the temperature, then we would have a shift to the left, which would mean even less of the water is ionized, right? Because we would be going this way, so less ions, more regular water. That means less of this, less of this. So our Kw would go down. Okay, that means lower H+, which means less acidic. If we went to 1 degree Celsius, our Kw would be 1.1 times 10 to the negative 15. And we can calculate the pH using our Kw. So we would have Kw is equal to 1.1 times 10 to the negative 15. And that's, of course, equal to our H+ times our OH-. We know that these two are going to be equal to each other in water, H+ and OH-. So we can say that our H+ concentration is equal to the square root of 1.1 times 10 to the negative 15, which is, and then that gives us a pH of 7.48. Okay, we can do the same thing. Well, we're going to do a little opposite here. At 90 degrees Celsius, the pH of water is 6.21. Calculate the Kw. So that's going to go back the opposite way. So if the pH is 6.21, the H+ we know is 10 to the negative pH, which is equal to 6.2 times 10 to the negative 7. So we know that that's the H+ concentration and also the OH- concentration because it's going to be equal in water. So Kw is going to be equal to 6.2 times 10 to the negative 7 squared, which comes out to this. So this is all stuff that you already know how to do. Finding concentration, Kw, pH, all of that. But it's just important for you to realize that if the temperature changes, these numbers for water can change. Okay, so keep that in mind when you're reading these types of questions. So now we're going to talk about predicting the strength of acid and base. Actually just acids, excuse me. We've talked about this briefly in class already. We kind of did a little bit of a preview to it with a question that we went over as a class, and now we're going to actually put this into practice. So we're going to talk about 3 different groups of acids throughout this course. One is an oxyacid, which you can see obviously have oxygen in them. Binary acids are just H attached to a element. Now sometimes those H's, there might be more than one H, but it's always attached to just one other thing. Carboxylic acids are organic acids, and they always have this thing at the end, the COOH. We'll talk more about those later on. So the three factors that we're going to look at are polarization of the bond, length of the bond, and then stability of the conjugate base, which we'll do later. So here, which acid is the weakest? For these are, you can see these are all the same except for the number of oxygens. So they're all HBr, and then different numbers. For oxyacids, the more oxygens you have, the stronger the acid is going to be. More oxygens have more electron drawing power, right? Oxygens, say oxygen compared to hydrogen. Oxygen is way more electronegative. So that means the more oxygens you have, the more electrons that are going to be pulled towards those oxygens. That means that the hydrogen isn't held on as tightly. So the OH, because all of these are going to have OH bonds, okay? If the oxygen is pulling the electrons more this way, then this H is not going to be as tightly held and it can more easily escape. That means the acid's stronger. The more easily a hydrogen can escape means the stronger acid. So here, our strongest acid is going to be this one. That means our weakest is this one. So another thing, so this is before we get to the other thing, this is just an explanation of what we just talked about, okay? The more oxygens you have, the more easily this H can get taken off. And that's what we want to happen in an acid. And then this little bit, also the additional oxygens help to stabilize the conjugate base. We don't really need to worry too much about that right now. So let's do another type of question. This said, which acid is the weakest? This is the same number of oxygens, but different central atom. So for this one, what you can look at is the electronegativity of the elements. This is going to be a stronger This one is going to be a stronger acid because this is more electronegative. If this is more electronegative, it's pulling more of the electrons towards it. So it means the H can jump off more easily. That makes it stronger. So the answer here, the weaker one, is this. So that's oxyacids. Now let's talk about our binary acids. If we're looking across a period, the acidity of binary acids across a period is going to increase. And that's because of electronegativity. So these, phosphorus, sulfur, chlorine, are all in the same period. So as we go across, it's going to increase, so this one is the weakest. And that is the same explanation as the oxyacids. As you go across a period, the more electronegative element is going to pull electrons towards it, so the H can just leave easier. The difference comes into play here. So here we have HI binary acids, except these are all in the same group. As you go down a group, it gets stronger. And that's not because of electronegativity, because you know that fluorine's the most electronegative element. So if you're thinking of electronegativity here, you're thinking, oh, that must be a pretty strong acid, HF. But it's not. Because what you talk about down a group, just like in honors chem when we talked about trends, you don't talk about electronegativity or effective nuclear charge down a group. You talk about size down the group. So here, this one is going to be stronger, and this one will be the weakest. That's because HI is the biggest atom. Okay, as you go down a group, the atoms get bigger. So I is going to be the bigger one, which means it's harder for it to hold on to that H because it's so far from the nucleus, and like the cloud is going to be bigger. It's going to be harder to hold on to it. When it's harder to hold on to it, that means it's a stronger acid because H can get away easier. So here we go with binary acids. Okay, so this is just binary. This is not oxy. As you go across a period, you increase acid strength. As you go down a group, you increase acid strength. And then its conjugate base is going to be the opposite. We already know that. So here is binary acid, just a little summary here. Remember, oxyacids have to do with the amount of oxygens or the electronegativity. So here is a little summary. I put this in your notes as well. And you can see here. Now, what's not going to happen is that someone would try to combine these. Okay, you're not going to be asked a question that's like HBrO3 and HClO4. You know, like that's combining different central atoms and also different numbers of oxygens. So what you are going to do is when there's more oxygens attached to the same element, the more oxygens there are, the stronger the acid. When they're the same number, but they're different central atoms, the central atom is going to tell you the more electronegative central atom, the stronger the acid. Binary acids across a row and down a column are stronger. So which of the following acids can be oxidized to form a stronger acid? More oxidized means more oxygens. So we're going to look for ones that could include more oxygens here. H2SO4 has the maximum number. HNO2 could be HNO3 as well. HBrO2 can be O3, O4. And then this one can be O4. So if they have 4, they're kind of tapped out. So those 3 can be more oxidized. Which acid is the weakest here? We talked about this before, I believe. The biggest pKa is the weakest acid. So if you look at the pKa's here, hyperbromous has the largest one, so that's going to be the answer. So before we wrap up this video, just a quick note about polyprotic acids. Polyprotic acids, it says acids with more than one ionizable proton. It means they have more than one hydrogen. So the second H plus is never going to ionize as easily as the first. So you'll always have a smaller Ka value. So here, if the Ka values differ by a factor of 10 to the third or more, the pH is calculated by only doing the first ionization, but other ones can have Ka1, Ka2, and Ka3 if they have 3 hydrogens. So you will see that. All right, so you can see that here. This is just a list of what some of those polyprotic would be. So like carbonic, when it loses its first hydrogen, that's the Ka. And you can see that the second one is much smaller. It goes from -7 to -11. Phosphoric is going to have 3 Kas. We go from -3, that's strong. I mean, not strong, but stronger than others. It's not a strong acid, phosphoric, but that's pretty large Ka for a weak acid. And -8 for Ka2, and then -13 for Ka3. Okay, and then even sulfuric, which is a strong acid, so you can see Ka1 they just wrote large, and then Ka2 is going to be a little bit smaller than that. So as you go down, as you lose your protons, your Ka is going to get smaller. So a titration curve for a polyprotic acid looks like this. This is phosphoric, so we have 3 Kas. So you can see it looks like the titration curves that we've looked at before, except 3 of those little horizontal parts, and then we have 2 equivalence points. So this is going to be when the first H is neutralized, and this is when the second H is neutralized, and then the third one's over here. Third H is neutralized. So I guess technically 3 equivalence points, but I meant just the vertical part when I said 2. Okay, and you can see that as you go up, the pKa gets bigger, which you know means the Ka gets smaller, and it means it's a weaker acid. So after they start losing their hydrogens, the more a polyprotic gets weaker and weaker.